Hi, my name is Susan Metz, and I am the principal investigator of ENGAGE, a 5-year project funded by the National Science Foundation. Have you ever thought about why so many engineering students switch majors and what can be done to retain them in engineering? There is a significant body of research on student retention, and ENGAGE extends this knowledge into the classroom. We work with engineering schools to implement 3 strategies that make a powerful difference in students' interest and ability to succeed in engineering. The 3 ENGAGE research-based strategies are to improve students' spatial visualization skills, to increase interaction between faculty and students, and to use everyday examples that are familiar to students to teach engineering and science concepts, the topic of today's discussion, presented by Dr. Eann Patterson, who I'm delighted to introduce. Eann is the A.A. Griffith Chair of Structural Materials and Mechanics in the School of Engineering at the University of Liverpool. At Michigan State University, he chaired the Department of Mechanical Engineering for 5 years. Eann is a strong advocate for using everyday examples when he teaches engineering concepts because they help students learn, and you will hear more about this right now. Eann?
Welcome. It's good to have the opportunity to talk to you today. You know, people ask me why I became so interested in formalizing these everyday engineering examples. I've used everyday examples in my teaching for many years. I see how engaged students become when I use this approach, and I wanted to make it easily available for other faculty to implement in their classes. So let's get to it. I'd like to first of all outline the presentation that I'm going to give to you. It's in 3 parts. First of all, an introduction, where I'll introduce you to some of the pilot study results we got, and then I'll also talk about the pedagogy that underpins our approach to teaching. And in the second part, I'll show you some everyday engineering examples and talk about what is everyday for our students. And then the third part, I'll talk about how to engage our students, how to attract and hold their attention. So let me start with the pilot study. We found that significantly more students rated their learning as high or significant than in the control class when we used everyday engineering examples. We also found that the overall value of everyday engineering examples contributed very highly to their understanding. And a key point that we found, which I'll come back to later, is that the learning was independent of the level of difficulty in our everyday engineering examples. So how do people learn? I'd like to talk about some research that Professor Kolob did in the 1970s. He plotted on the x-axis doing and watching, and he called them active experimentation and reflective observation. And then on the y-axis, he plotted feeling against thinking, and he called these concrete experience and abstract conceptualization. And then he said that some people learn by doing and feeling, and he called these people accommodators and plotted them in the top left corner. And then as we move around this plot, some people learn by watching and feeling, and he called them divergers. Others learn by watching and thinking, and he called them assimilators. And then the fourth category, convergers, learn by doing and thinking. It's our job as faculty to help students learn, and this has been nicely summarized by Adams and Felder. They said the educational role of faculty is not to impart knowledge, but to design learning environments that support knowledge acquisition. And I'd like to add to that for all students. So everybody around Kolob's 4 quadrants there. Now some of you may have been muttering that you learn in different ways at different times. And that was recognised by Honey and Mumford. And they modified the Kolob scheme a little piece. They kept the axes with the labels, doing versus watching and feeling versus thinking, but they said that we cycle round the quadrants during the process of learning. And so we tend to start in the doing and feeling quadrant, having an experience, and he called that being an activist. And then we progress to reviewing the experience, and they call that being a reflector. And then from there we move to concluding from the experiences, being a theorist, and then the final quadrant, being a pragmatist and planning the next steps. There's a key word here, experience. And I'd like to suggest that we can use everyday engineering examples to give students those experiences. Albert Einstein said, Knowledge is experience. Everything else is just information. Our students have very limited lab experience and probably no industrial experience these days. So our task is to find their common experiences and to use them to illustrate engineering principles. Everyday engineering examples provide a pool of common experiences. So if we go back to Honey and Mumford's schematic and consider each of the quadrants, then we can take the everyday experience that the students have already had outside the classroom before they come into lectures and use that as the first part of having an experience. The instructor can review that experience in class, perhaps do a demonstration to remind them and connect them with their memories. And then the third part can be an activity done by the student or by the instructor. It could be part of homework or it could be part of an assignment done in the class. But then the fourth part is student-led, planning the next steps. And what we'd like to think is that having seen how their common experiences can be used to explain engineering principles, that next time they have that experience, they look at the things differently and begin to learn from that experience in new ways. One of the things we have to remember is that things are very different from when we were students. There's an enormous gap between our experiences today as professors and our students today in their capacity as young people, but also between what we experienced when we were young people and what they experience today. The gap is so large that is warranted an anthropological study that has been published by a lady called Rebecca Nathan in a book called My Freshman Year. She took a year off as a sabbatical and went to another university and became a freshman student and studied the relationships freshman students have with their studies and with their professors. And let me illustrate how things have changed. Here's a Brownie box camera. Some of you may recognize it. That was given to me by my father when I was about 6 or 7. And here's a little digital camera that I gave one of my children when they were 6 or 7. That's about 7 or 8 years ago. So it's not the latest model. But nevertheless, you can see the contrast is enormous. And of course, today our students are carrying around a digital camera in their iPod Touches all the time. They're probably taking pictures of you whilst you're giving lecture. So let me talk a little bit about what we mean by everyday engineering examples. We mean things that are familiar real-life objects and situations that we use to illustrate engineering principles. The level of idealization needs to be minimized to retain relevance and context. And the choice of examples is critical. There needs to be a transparent connection to students' experience. But there also needs to be a basis for straightforward implementation of the engineering principles. So we've put together a couple of essential attributes to help you identify suitable examples. And our first attribute is that examples need to be familiar to all students. So using sailing boats to teach vectors might work in Maine, but it's not going to work in the Midwest where they may never have seen a sailing boat. Or using an example of walnuts falling from trees to illustrate kinematics of particles might work in a tree-lined rural campus, but it's probably irrelevant for an urban inner-city university. Students may panic about the context and then fail to listen to you. Our second attribute is that you should pose questions with useful or interesting answers. The absence of a useful or interesting endpoint creates a tedious intellectual exercise, and students can spot those a mile away. So some research has shown that the perceived usefulness of learning influences students' motivation. So this quote from Doris Lessing nicely sums up what we're trying to do. She said, "That is what learning is. You suddenly understand something you've understood all your life, but in a new way." And that's really what we're trying to achieve with our students. We'd like them to look at an experience they've had perhaps every day of their life and understand new things in it, new engineering principles. So now I'd like to move on and show you some engineering examples that we have developed. So my first one is Winnie the Pooh. And this is contributed by Chad Young of Nicholls State University. You'll find all the details I'm going to talk about on our website at www.engageengineering.org. And so if you take a Winnie the Pooh book and open it to the first chapter, you'll find a nice picture here of Winnie the Pooh disappearing, holding a balloon. And what Chad suggests is that you show a video of this, and he gives you the link on our website so you can follow that, and then show it to your students and discuss buoyancy with them. And when you've done that, ask the students to calculate the number of helium balloons that they would need to lift them in a lawn chair. And when they've done that, they can compare their answers with a nice video that Chad has provided for us on YouTube. So if you go to the link he provides, you'll find a video of a Mad Hatter sitting in a lawn chair being lifted up by a huge cloud of helium balloons. And so they can compare their answers with what was actually required in reality. So our second example is for freshman engineering graphics. It's called Cartons and Boxes. This was contributed by Cheryl Sorby of Michigan Tech University. And again, you'll find it on our website at engageengineering.org. And she suggests that you take some old cereal boxes into class and distribute them amongst the students. And have the students estimate the volume and the surface area of the box. And then when they've done that, ask them to disassemble the box and measure the area of card in the box and see how that compares with their estimate from the assembled box. And then you can also collect in some disassembled boxes from the students and tessellate them together and talk about how manufacturers can minimise waste in the way they arrange their boxes when they're cutting from the cardboard sheet. I have now a quote from Eric Clapton, not one you'd perhaps expect from him, but he said, "It's very hard, so I try and make it as engaging as it can be. But you have to face the fact that no matter how good it is, you can only hold their attention for a little while." He was talking about his small children. And I think those of us who have had children will all agree with him that it's extremely difficult to hold their attention for more than a short period of time. And it doesn't get much better as they become teenagers and appear in our classes. And so what I'd like to talk about now is how to engage our students using our everyday engineering examples. So to help you engage your students, we've developed a series of lesson plans which are described in a set of booklets. With 4 booklets, and I'm going to show you 4 examples, one taken from each booklet. My first one is about frying up some sausages. It's related to sophomore mechanics of solids, and the topic is Moore's circle of stress. And the suggestion is that you take a portable hot plate into the classroom and cook some sausages and share them with the class. And you should certainly have their attention when you do that. But before they eat, ask them to look at how the sausages split longitudinally, and then discuss the stresses acting in the pressurized skin of the sausage and construct a Moore's circle of stress for the skin. And then you can eat them. Very nice. So our next example is related to sophomore thermodynamics, and we've called it Cupcakes with a Candle. The topic is reacting mixtures and combustion, and our suggestion is that you take a cupcake and a candle and a glass jar into class. And then light the candle and invite sealed bids on the time it'll take to extinguish the candle when it's covered with the jar. So if you're watching this with a group of people, you might like to have your guess now. And you can discuss the combustion of paraffin and the value of energy emitted, because these candles are principally made from paraffin wax. And so in a jar this size, it'll take about 15 or 20 seconds for the candle to go out. There it goes. And so then you can give the cupcake to the winning student. And I think you'll have their attention if you do this sort of demonstration in class. And then once you've done it, you can invite students to calculate the quantity of natural gas required to cook a pan of pasta back in their residence. So our next example is for dynamics courses. The topic is free and forced vibrations. And we suggest you take a ruler into class, clamp it down onto the bench and flick the free end. So you get a nice noise like that. You can also slide it up the bench so the pitch changes. And the frequency will go up. Then you can invite the students to repeat the experiment themselves. And of course the class will erupt into a lot of noise and enthusiasm. and you've got them engaged. Then you can show students how to equate kinetic and strain energy to find the natural frequency of the ruler. And when you've done that, you can ask the students to repeat the analysis for themselves, but this time to use a whip antenna with a ball on the tip, so they can evaluate their own understanding of the topic. Our next example is called soap bubbles. It's designed for a fluids course, and the topic is the property of fluids. And what we suggest you do is invite students to blow some bubbles using a straw and some detergent solution. So let's see if we can get some decent bubbles. There we go, so there's nice bubbles there. So when they've done that successfully, you can ask them to draw a free body diagram for a section of a spherical stationary bubble. And when they've done that, you can discuss the surface of the fluid behaves like a tension membrane, and explain that the detergent acts like a surfactant with local variations in concentration, allowing changes in tension to accommodate shape changes. So you can see where the bubble is contouring around the end of the straw, it's not quite spherical, and it can hold that shape as a consequence of the detergent acting as a surfactant. So to conclude, let me recap on some of the results we found from our pilot study when we implemented these ideas in our classes. First of all, we found that significantly more students rated their learning as high or significant than in the control class. Secondly, we found the overall value of our everyday engineering examples correlated very highly with contribution to understanding. And thirdly, that the learning was not tied to the level of difficulty in our everyday engineering examples. And then there was a fourth result that I didn't share with you at the beginning, but which is very important to us as instructors. And that is that teaching effectiveness was rated significantly higher compared to the control classes. So not only will our students learn more effectively, but they'll also rate you and your course more highly. Plus, you're going to have a class that's more engaged, and I think all those things are rewarding for us as instructors. So think big, start small, act now. And to help you get started, we've provided a plethora of resources on our website. So please go and have a look and see if there are examples in our database or in our booklets that can help you use an everyday engineering example in a class tomorrow. Thank you.